Welcome to DWBIADDA channel. Please subscribe for latest training videos.
Hi, and welcome to the session on the linear regression using gradient descent. So in linear regression, as we already know, we do a regression where we try to fit a straight line through a data and we try to predict a value. But we need to have the best fit line which best predicts the values. To do that, we have something called the mean square error. The lower the mean square error, the better the model is. In other words, the lower the errors, that is the gaps between the actual value and the predicted value, the better the model is. Now, different linear regression models have different ways to get this done. Most of them use something called gradient descent, which is nothing but an iterative way of finding the best fit for a line. Let's try to understand what this gradient descent is. Let's take an example. So in the data points x1 to y1, which is extending up to xn, I'm trying to find a value of y for a value of x. Data points are from x1 to yn, x1 to xn, and y1 to yn. I want to predict the yi for a given value of xi. To do that, I'll have a function, and if based on this function, I'll be able to predict a value of y. That's the normal linear regression. Now, what's gradient descent? So let's try to have the model, or the very base model, along with this function, and try to improve on it as and when we are moving forward. So in order to do that, we'll have a very basic model generated first, which will be, let's say the prediction for the values of x is the average of it. So we'll have a function which is f0, and we pass the value of xi, and this will predict the value of y, which is nothing but the mean of it. Now, this is not a good model, I know that, but I need to slowly improve my model. So how do I do that? To do that, I first calculate the residue. Residue is nothing but the actual value of y minus the predicted value of y. In this case, the predicted value of y is the mean of the entire data set I have in x1 and y1. So my predicted value will be y0, and the residue will be each individual data point minus the average of it. I'll call that as the residue. Now, in the next step, instead of training my data set on the value of y, I will try to train my data set on x1 and y minus y01, which I found it over here, which is nothing but the average of it. The next y2 minus y01, and it goes on till xn and yn minus y01. So that's how I will try to plot my next function. So my next function will be f1 xi. Xi is the input for the new independent variable, and my prediction will be y minus yoi, which is nothing but the average of it. So this is what I'm going to predict. Now I have two functions. This is one function and this is another function. Let's try to sum it up. So f0 plus f1 gives me y0i, which is nothing but the average, plus y minus y0i, and if I sum it up, I'll get only y. These two will cancel each other. So this clearly means I'm getting a better value of y. Now I keep repeating this until I get a good value of r square, and this value actually stops decreasing and my precision actually increases. So we call this as a gradient descent curve. We call it the valley, which is the lowermost point. This is the best possible fit where we have the valley at the 0. It slowly gradually decreases and finds the point where it has the lowest error, and again it moves. Now this would be the point where I would like to have my model built. Alright, let's try to look at the same thing in a code. I would like to build a gradient boosting classifier that will be for a linear regression, and I would like to have the best possible fit over here. Okay, so now there are certain things which I need to take care before I run a code. For example, the first one is the learning rate. Now, what do we mean by a learning rate? Learning rate is the rate at which it learns. You can take it as the steps in which it will learn. So in that, so we can understand that higher the learning rate, the better the performance of the model, but not accuracy. When I say performance, it might run quickly, it might have a good performance, but not a good result. The lower the learning rate, the better the result is. And we'll have to do a trade-off between the estimators and the learning rate. Estimators is the number of iterations it would run. So that would again um, have an impact on the performance. So that's a trade-off which we have to make. Okay, so I set the param grid where I define the learning rate. I set it as a list of 0.2, 0.6 and 0.9. We can have much longer list as well, but to keep things simple, I have kept it as 3, and I have few subsamples as well. Now, what do you mean by subsample? Subsample is nothing but individual models are built on random set of samples. It's not the same sample which will be always be trained on. So it will randomly build individual models to train on. So that makes the model, the training, more versatile. All right. Now I apply the gradient boosting classifier. I give the max depth and the number of estimators. I've given it as 200 over here. It can be more as well. To keep things simple, I have kept it as I will stick to 200. So once I run this, I will have to define a grid search. In the grid search, we have a nice function where we can pass the model in which we are running. Here we have defined it as a GBC. I give the crossfolds. I have defined as 3. Param grid is the param grid which I am trying to pass over here. The scoring parameters, I have chosen it as ROC AUC, which is nothing but the area under the curve. And the train score is true. I would like to have the training score of it, and the verbose is equal to 1. Now I do a grid search fit with the train data and the X train and the Y train data. That gives me a nice result. Let's see what the result talks about. All right, so if I see, I have the mean fit time, mean score, mean test score, mean train score. These are the different parameters which are published by the results, and these are the parameters which it has run, and it has given a rank test score as well. So these are the different parameters which I can actually walk through, a lot of parameters on them, and based on these I can choose which would be my best model and what would be the sample, the subsamples, the learning rate, and what would be my iterations, right? So I can give a holistic view of the best fit over here. Let's try to have things in a plot that makes things easier to understand and makes our life easier as well, right? So okay, so I will build a plot on 3 different subsamples. One is 0.3, one is 0.6, and one is 0.9, right? So I take the Y label as AUC, and I do plotting between the AUC and the learning rate. Let's see how my AUC, which is nothing but the area under the curve, again it is nothing but the parameter based on which I would choose how efficient my model is. How does that change based on the learning rate? It's pretty clear from here that the best performing model is the subsample 0.3. It covers the highest learning rate, which means it goes to the deepest point of the valley. We call this as a valley. All right. So now we can conclude from this that the lower the subsample ratio, the model performs the better. But again, there is a trade-off. We have to have a trade-off between the number of estimators and the learning rate, because the more the learning rate, the lower the learning rate, the higher is the hit on the performance of your code from the end-to-end running. So that's a trade-off which you have to decide based on the number of iterators, the subsamples, and the learning rate, right? So this was about the gradient descent, and hope you had a good learning. Have a good day.